In this video, we're going to talk about some properties of group homomorphisms. So for the duration of this video, we're going to let phi from G to H be a group homomorphism from a group G, whose operation will be called dot, to another group H, whose operation will be called star. And it's possible G and H are the same group, and it's possible that even if they're not the same group, they have the same operation. But just for full generality, we're going to assume that they're different groups, or possibly different groups, and have possibly different operations. All right, so I'm going to make 4 claims here, and we're going to prove these 4 sequentially in this video. Number 1, we're going to prove that phi of the identity element of G has to be the identity element of H. In other words, phi has to map identity elements to identity elements. Number 2, we're going to prove if X belongs to G, then phi of the inverse of X in G is equal to the inverse of phi of X in H. So again, just for clarity, here we're taking an inverse in G, and then here this is taking an inverse of an element of H. That's number 2. Number 3, we're going to prove if X belongs to G and N is an integer, any integer, positive or negative, then phi of X to the N is equal to phi of X, all of that raised to the nth power. In other words, phi has to map an nth power to an nth power of something, and that something is phi of X. And finally, we're going to prove if X is in G, and the order of X is finite, and let's let Y equal phi of X. I'm going to prove that the order of Y has to divide the order of X. So these will be the 4 things that we prove. Each proof is going to be fairly short because we're going to use a lot of facts that we've proven previously here. Now, one thing I want to suggest, as always, when there's a litany of proofs in one of these videos, is you should just stop the video now, stop listening to my voice. You don't enjoy it that much anyway, admit it, and try to prove the 4 theorems. If you can prove the 4 theorems on your own, then there's not really much need to watch the video, unless you want to see how my argument contrasts with yours. But definitely, please stop the video and try to prove the theorems. Okay, I'm going to move on because I don't want to make this any longer than it already is. All right, so let's do the proof of number 1. All right, here's how this goes. We know that the identity of G is equal to the identity of G times the identity of G. And I'm using dot there because I'm multiplying elements in G. So because of that, I can take phi of each side, and because phi is a function, it has to map both of these to the same thing. All right, so I know that phi of the identity is equal to phi of the identity times the identity. But then I can rewrite the right side because I know phi is a homomorphism and preserves multiplication. It's going to be the product of these 2 things. Now notice I'm using star now because phi of the identity is an element of H, and elements of H get starred, not dotted. Okay, so now I'm at a point where I have that this element here is equal to this element times this element, which suggests that this should probably be an identity because it's taking this element here, multiplying by it, and producing the same thing. But now, remember, the definition of identity is that for this to be the identity, it has to multiply by every element of H and give the same element back. So I can't just look at this and say, oh, that makes this an identity. I have to do a little bit more here. So the little bit more I'm going to do is I'm going to go ahead and multiply each side on the left by the inverse of phi of 1 in G, phi of the identity of G. So we're going to multiply by the inverse. Again, that's a star. And we're going to do the same thing on the right side of the equation. And of course, the operation in G is associative, so I'm not going to worry about which 2 of these get grouped together. And at this point, these 2, since these are inverses, these are going to give us the identity in H. And over here on the right, I'm going to have the identity in H starred with phi of the identity of G. And at this point, just one more step left to do. I'm going to leave the left side the same, And because here I have the identity in H, that's going to multiply by this and just give me back phi of the identity in G, which is what I wanted to show. All right, so this tells me that phi has to map the identity of G to the identity of H. Okay, that's the proof of fact number 1. Okay, now what about fact number 2? Let's just review what fact number 2 is. Fact number 2 says x inverse gets mapped to the inverse of phi of x. All right, let's switch colors for this one. Let's do a nice little dark green color. How's that? Okay, here's the proof of number 2. So again, I'm going to start by just setting up a fact that's convenient for me. Here I started with the identity of G equaling itself times itself. And I'm going to do the same little game here where I write down the identity of G on one side, and then I write down on the other side, I write down something involving x. So let's do x times x inverse. Again, that's a dot because this is an operation taking place in G. All right, I'm going to hit each side with phi. Phi is a function, so I should send both of these to the same thing. And now I'm going to use the homomorphism property. Actually, a couple of homomorphism properties. First, I'm going to use the homomorphism property to split this up, because I know that phi preserves multiplication. And now I'm going to use property 1 that we just proved and say phi of 1 in G has to be 1 in H. It has to be the identity element of H. So now I know that phi of x inverse multiplied on the left by phi of x has to be the identity. So I think this is going to be pretty straightforward at this point. I think I can just multiply on the left by this thing, by the inverse of phi of x. Do the same thing over here. And now this is going to give me the identity in H, because that's a multiplication of two inverse elements. And over on the left, I'm just going to be left with phi of x inverse, because this other element here is the identity. It's not going to do anything to this. So over here I have identity of H times phi of x inverse. And then at that point, I think I know that phi of x, all of that inverted, equals phi of x inverse. So I think I can check off property 2 now. Okay, what about property 3? Property 3 was that phi of x to the n equals phi of x, all of that to the n. So let's see if we can prove that over here. Let's see, I'm going to switch to a different color now. This will be the proof of number 3. All right, so for this one, I'm going to start by using induction on n to prove that this statement is true. We're going to prove that phi of x to the n equals phi of x, all of that to the n, for all natural numbers n, and then we'll do it for negative integers. So for natural numbers, so we're going to prove this first for natural numbers n. Okay, for n equals 1, I think the statement is true automatically. Like we know that phi of x to the 1, that's just phi of x, and phi of x, all of that to the first power, that's also phi of x. So these are the same, and that's what I want. All right, so now let's assume that this statement is true for n equals k. In other words, let's assume that phi of x to the k equals phi of x raised to the k. Let's put that in square brackets again. Okay, then we will prove that this equality here is true for n equals k plus 1. In other words, we're going to prove that phi of x to the k plus 1 is equal to phi of x, all of that raised to the k plus 1. All right, well, let's just do the most obvious thing that there is, which is let's express x to the k plus 1 in terms of phi of x to the k times x. Okay, I'm not saying that's totally obvious. It's just the only thing I know of to relate this to x to the k. I want to get an x to the k in there, so I'm going to try writing this as a product of two powers of x. All right, and now I can use the homomorphism property and say, well, that's phi of x to the k times, and that's multiplication in h times phi of x. And I know by my induction hypothesis that phi of x to the k, that's phi of x raised to the k. And I'm multiplying that by another phi of x. And again, that's by the induction hypothesis. And just a side note, we haven't done a lot of induction in this course yet. We're probably going to do more later. But when you do an induction proof, state clearly where you're using the induction hypothesis, because that's usually the least obvious step in the proof as to why it's true. But now I have phi of x to the k times another phi of x. Well, that's just phi of x all raised to the k plus 1 power, and that's exactly what I want. Okay, so this statement this is true, and that concludes the induction step. So by induction, I can at least say phi of x to the n equals phi of x to the n for all natural numbers n. Okay, now what about other integers like 0 and negative numbers? Well, let's just quickly record what happens with those. I know that phi of x to the 0, that's just phi of the identity, because x to the 0 is the identity of g. Phi of that has to be the identity of h by property 1. And then that's the same thing as phi of x raised to the 0, no matter what phi of x is, because anything in h raised to the 0 power is the identity. Okay, so that checks that off for n equals 0. What about n, a negative integer? So let's assume that k is a natural number, because now I'm going to represent n as negative k. So then phi of x to the negative k, well, that by definition is the same thing as phi of x inverse to the k. That's the definition of x to the negative k. But then, because k is a natural number, now I can say that's the same thing as phi of x inverse all raised to the k, because I already proved this statement, this equality, for positive integers k. So even though I was really proving it for x, the reasoning would work also for x inverse. There's nothing special about x. So I think I can go ahead and say this is true because k is a positive integer. But now what is phi of x inverse? Well, by property 2, that's phi of x inverse, and all of that's being raised to the kth power. Again, this is by the property that we just proved, that the inverse of an element has to get mapped to the inverse of phi of x. But, well, what is that? That's really just the same thing by definition as phi of x to the minus k. Okay, so now that shows that x to the minus k, that is x to a negative exponent, has to be phi of x to that same negative exponent. So I think that proves property 3. It's a little bit, like I haven't written quite as many words as I might like to see in one of your proofs, but I hope that conveys the idea pretty well. All right, and finally, let's come back to property 4. Property 4 was about orders. And I think we were supposed to show that if phi of x equals y, and the order of x is finite, then the order of y has to divide the order of x. For this, one thing that you might remember, something about orders, is that one way we can establish that this divisibility statement is true, if this is an order, is to show that y raised to this power is the identity. Because we have this old theorem that says if y to the k is the identity, in this case it's the identity of h, then the order of y has to divide k. So that's going to be our game plan. Is we're going to show that y raised to this power, the order of x, has to be the identity. All right, so let's just try writing that down. What is y raised to the order of x? Well, recall that we defined y to be phi of x, and we're raising that to the order of x. But now by property 3, one thing that we know, that's the same thing as phi of x to the order of x. Okay, now I realize this is the first time we've really seen this notation like this. It's kind of kooky looking, like x to the, it looks almost like x to the x, or x to the absolute value of x. But remember, that says x to the exponent, which is the order of x. If I raise x to the order of x, that's the identity. That's by definition of order. So that's the same thing as phi of the identity element in G, which we know by property 1 is the identity of H, which is just what we wanted to show. So since y raised to this power is the identity of H, this means that, well, first of all, that means that there is a finite positive integer, power of y, which is equal to the identity. So y has to have finite order. So I'm going to write that down. That means this is finite. And furthermore, by that theorem I just referenced, we know that the order of y has to divide the order of x, because this is an exponent that takes y to the identity. So it has to be divisible by the smallest exponent, which takes y to the identity. I still feel like looking at this feels very strange, this way of writing it. So one thing you might do, and it might make the proof read a little bit more comfortably, is give the order of x a name, like call it n or something, and then maybe even give y a name, call that, I don't know, I guess maybe you could call that k. I think I was using k for the order of x here, so maybe switch the names around. But anyway, the point is give each of these a letter name, and then I think the proof will read a little bit more like what you're used to. Okay, so what do we have here? We got 4 beautiful properties of homomorphisms, all of which are going to be useful in determining whether a homomorphism with given properties can exist.